Okay, so today we are going to start talking about exponential and growth and decay models. Just a reminder that an exponential growth looks like this picture, right? And an exponential decay looks like this picture. And we're going to kind of use this basic model where y is equal to a naught is what we say, e to the kt. Now this is really exactly the same thing as the PERT equation. It's just that instead of r, we're using k to indicate our growth rate or our decay rate. And a naught is the initial quantity because whenever I put in time 0, this whole thing goes away and just leaves me with y equals a naught. Okay, so a naught is always our initial quantity. Now the whole reason that we've been learning all these different kinds of functions is so that when we get out in the real world and we have a bunch of data, you know, maybe we're a scientist, maybe we're a business person, maybe we're whatever, we have a bunch of data and we think, oh, look, I want to use this data to predict something. Well, we need to be able to look at a picture of that data and see, does it look like there is a pattern to it? And if there is, how can we model it? And that's where knowing what all these functions look like and how they behave can help us. So one of the biggest ones that people use a lot are these exponential growth and decay. Okay, so basically, you know, we've already seen this, right? The PERT, that's for like continuous growth, and really this is the same thing, it's just continuous growth. Usually we use this one specifically when it comes to investing money. This one we're just using as it's still considered continuous growth. And then this was the one that we used for compounding. Now this one is not quite, we're going to use more the E model here. But so basically whenever an amount grows or decays at a fixed percentage per unit of time, so it grows 5 units every hour or something like that, then that is a growth or decay that's exponential. So it's like that repeated, it's doing this every so often a unit of time. Okay. So let's just dive in here and look at an example of how we can use this, okay? So we have a population of bacteria that's doubling every hour. If the culture started with 25 bacteria, we're going to start with the model that represents this function. So we want to come up with basically an equation that looks like this, okay? So the easiest thing to figure out first is that we know that the culture started with 25 bacteria. So if we want to think of this as our y equals, right, then we have a naught e to the kt, okay, and we know that basically this started with 25, and really t is time, and in this case it's t is in hours because it states it. Right. So basically, we figure out what t is based upon the amount of what we're talking about. It could be every 5 minutes. So then it would be in minutes. It could be every 6 days. So t could be in days. It's however basically it's defined here as every blank. Right. So what this first part starts saying, the culture starts with 25 bacteria, means that y of 0 is equal to 25. Okay. So that's going to give me a naught is 25, because if I plug in t as 0 here, right, t, it's going to take out this entire thing, will become 1, and basically y is a naught. So essentially that gives us our first piece of equation, which is y is equal to 25 e to the kt. Now we want it to be in function of t, so the t is going to stay there, but we need to find what k is, and that is our doubling rate, okay? And so we kind of think of it, so this other piece says if the culture with 25 bacteria, it doubles every hour. So that means that, I mean, we could actually pick any number, but the easiest one would be after 1 hour, then this would be 50, right? Because it says it doubles every hour. So what we can do here now is we can use this as an ordered pair. So 50 is y, x is 1, and t is 1, I should say. So that means I'm going to have 50 equals 25 e to the k, and then our 1. So basically, we're just going to have 50 equals 25 e to the k. All right, so the first thing we should know from solving these before is I'm going to divide by 25 here and get 2 equals e to the k. And now I need to solve for k, so that means I'm going to take the natural log of both sides. And when I do that, I get the natural log of 2 is equal to k, because the natural log of e to the k is just k. And that is my growth rate. Okay? All right. So that gives us, I can now substitute the k in here. Okay, so then we have y equals 25 e to the, actually let's just, because we're going to need it in the next part, let's put in ln of 2 here. We're going to carry it out to multiple decimal points. So based upon this, I'm going to put e to the 0.6931 t. So then we can use that for our next thing. So this is part A. We found this. We found the rate, and it was because we knew that it doubled every hour. Right? I could have put in y of 2 would be then 100, right? But, I mean, obviously the first hour was the easiest. All right, so now it says, how long will it take for the population to reach 75? So now we already know, because we're talking about the same population, we know that this is the formula. So when will it reach 75? So basically we're looking for y of what equals 75. Whoops, sorry about that. Okay, so that means I'm going to essentially solve for t and put in 75 here for y. So I have 75 equals 25 e to the 0.6931 and then t. So the first thing that I'm going to do, again, every single time, is I'm going to divide by this number in front here. I'm going to divide by 25, and I'm going to get 3 equals e to the 0.6931 t. Now I'm going to take the natural log of both sides, and this will just end up being the natural log of 3. The natural log of e to a power is just the power, so I get 0.6931 t. And then I am going to take this and divide to solve for t. Okay, so t is approximately, let me put this, now this is the exact answer here. Well, it's actually not exact because I've already, really this should be ln2 if it's exact. So I'd have ln3 divided by ln2. And so basically I'm going to put this in my calculator now as the natural log of 3 divided by 0.6931. This gives us approximately 1.59, and then this is hours because our t was in hours. So a little over an hour and a half, right? Because 1.5 hours would be 90 minutes. Okay, so that's how we approach these. Okay, so basically we start out with this basic equation, right? We figure out what A naught is. Hopefully we have another information so that it'll help us find K. And then once we write the formula, then we can use it to find out anything about that one. Okay? All right. So here's a science application here. So the half-life of carbon-14 is 5,730 years, and we're going to express the amount of carbon-14 remaining as a function of time t. Okay, so we're going to start out with this. Y is equal to A naught e to the kt. Now when they don't give me how much of something I have, I just go with like A naught is like 1. So it's like 100% of something, so I just think of it as 1 unit. So we're going to just use y equals 1 e to the kt in our case, because they didn't give us a specific, they just want basically how to break this carbon down. Okay, so I'm just going to use 1 in this particular case. So I know that the half-life is 5,730 years. So that means basically my t is 5,730 years, and then if I started out with 1 unit and I want the half-life, then this should be equal to, if I started out with 1 unit, I should have a half over here. So that's my 1/2 equals e to the my k, and then times 5,730. So that's how many years. So my t is 5,730 years. And if I started out with 1 unit, I'm going to end up with a half. Now, if you notice back on this other particular one that we just did, you know, when we came over here, we actually used this initial. We used 25, so then to double it, it was 50. You know, I could have just started out, and I would have gotten the same thing with 1, and if it was double, it would be 2, so I could have just started out with this. I'd get this exact same thing if you go back through it, because initially I'm going to have, basically, if I take the natural log, I immediately get natural log of t equals, and then our t was 1, so we'd get e to the k. So basically, we end up with this right away without having to divide, because the first step is to always divide. So if we're doubling something, we should always end up with 2 over here. If we end up with a half of something, we should always end up a half over here. Right? If I'd started out with 10 units here, then half of it would have been 5. So then the first thing I'd do is divide by 10, and then I'd end up with a half. So whether I start out with 1 unit or the initial quantity or whatever, I'm always going to get the same thing. All right, so let's figure out our k now. So this is the natural log of a half, and this is, so when I take the natural log of this side, then this just becomes 5730k. I just wrote it because I like my numbers in front of my variable, because the natural log of e to anything is just the anything. So now I end up with this, and then I just divide by 730, or 5730. Now, I know if you read your books, like they'll give you formulas for half-life and doubling time and all that kind of stuff. I don't have room in my brain for all that. I just know I need to do this process, and I get it, okay? And there's all kinds of different ways that you can write ln. Like some people will, like sometimes the book, the natural log of half, could also be the negative natural log of 2, right? Because this is really, we could write this as the natural log of 2 to the minus 1. So then we can put the minus down in front. So like it doesn't matter how you put it in. I mean, there's lots of different equivalent ways to write it. Okay, so anyway, our k will be approximately then, if I put this in, I have the natural log of, I'm just going to put in 0.5 divided by 5730. This gives me approximately, okay, so now watch this, because this is e to the minus 4. So this says, it gave me negative 1.209, we'll go one more, 68, okay? That's what it gave me, but it was e to the minus 4. So basically that means that my decimal place is going to move back 4 units. So it'll be 1, 2, 3, 4. So basically I'm going to have my k is 0.0001, 2, and then I'll just go one more, 1. Because that's a lot of decimals. Okay, so my e to the minus 4 here, because my number was very small, so that means my decimal place basically is moved out. And I want to at least have 3 significant figures here. I mean, that otherwise I'm rounding too carefully. And okay, and it was negative. So now we have our formula. Okay, so I'll just write it down here as y equals, we're just going to use a naught in our particular case, because we'll just use it for any one. And then we have e to the k is negative 0.000121 t. All right, so you notice, maybe you notice, I hope, that for the growth, then my k was positive, right? It was 0.6931. When I'm shrinking, then my value should be, my k should be negative. Okay. All right, so then this will give us the formula. We just have to we just put in the actual initial amount, or we put in how much is left at the end over here, and then we can solve it. Okay, so let's use this next part. So use the formula to find the age of a bone fragment that contains 20% of its original carbon. Okay, so we want to think of, if this is 20%, then we want to think of this is 0.20 that's left. And so if we're talking percentage, then a naught is 100%, right? It's 100% of the original. I mean, that's how much was in the original, was 100% of its carbon. And so then that as a decimal is just 1. So we can just use 1 e to the negative 0.00121 t. And so really, I can just drop the 1. So I can directly go to ln, so natural log of 0.20 equals negative 0.00121t. I divide by negative 0.00121. Actually, I lost a 0 here and here, so let me add that in. And this should be my t. So my t will be approximately, let's put this in my handy-dandy graphing calculator. I'm going to put in the natural log of 0.2, close my parentheses, divided by negative 0.000121. And so we'll round to the next whole number, and that's 13,301. Okay? Approximately years, because this was in years. Okay? Because we started out with years up here, because it takes 5,730 years. All right, so now there's a lot more to carbon dating than just this basic formula. There's like different types and all this kind of stuff. So this is a little bit simplistic, but this is how it can be used.